The hardware of MC1322x Part 1, presented by the following members. Today we'll be talking about memory architecture, ROM and RAM, serial flash, GPIO, UART, timer module. Memory architecture. Memory architecture describes the different ways to implement data storage in a computer. Memory or storage is classified into two categories: volatile and non-volatile memory. Volatile memory is memory that gets lost when there is no power to the component, meaning it does not store any data permanently. For example, RAM is volatile memory. Non-volatile memory permanently stores the data written to it. Therefore, when the power is cut off, no data will be lost. For example, ROM is non-volatile memory. There are a few types of memory access methods. Random access memory is usually main memories in which each memory location has a unique address. This helps with speed and time, considering any memory location will take the same amount of time to access. Sequential access memory allows memory to be accessed in order, from one address to the next. Direct access memory is memory stored in tracks. Each track has a separate read-write pointer, so any time you want to access that specific memory, you just follow the pointer. The image of the pyramid describes memory hierarchy. The slower memory is at the bottom, and the faster memory is at the top. Auxiliary memory is used for storage, such as your typical mechanical disk hard drive. Primary memory is used during runtime, such as RAM. This also includes ROM, which permanently stores data, but is read-only memory, which is why it is still fast. At the top of the pyramid, we see cache memory and register memory, which is used to store program data, which is currently being executed in the CPU. This is the fastest type of memory. RAM and ROM. RAM is random access memory, which is volatile memory used by the CPU to quickly access and use information that will not be stored permanently. When the device powers off, any data in RAM will also be wiped. In the MC1322x, the RAM is divided into 4 blocks of RAM: RAM 0, RAM 1, RAM 2, and RAM 3. This allows the unit to save power. Individual RAM blocks can be powered off while the device is not in use. RAM 0 contains 8 kilobytes of RAM. RAM 1 contains 24 kilobytes of RAM. RAM 2 contains 32 kilobytes of RAM. RAM 3 contains 32 kilobytes of RAM as well. Any attempts to read or write to RAM requires at least 2 system clock cycles. Why is RAM divided into blocks? A portion of the RAM can be left on while sleeping for some data retention. At any time, there can be 8, 32, 64, or 96 kilobytes of RAM active. The reason why the RAM is divided into blocks of different sizes is to allow for different amounts of RAM to be active at a given time. Depending on the RAM that was left active while the device was not in use, the boot time may be longer upon restart. This is because the inactive RAM has to be reloaded from the flash memory, as it was not left on while the device was sleeping. ROM stands for read-only memory. This is non-volatile memory that cannot be written to. It can only be read, as its name suggests. When a device powers off, ROM is not wiped and will be available again upon startup. The MC1322x contains 80 kilobytes of ROM, which is 20 kwords. The ROM contains the bootstrap code that allows the device to boot up. It also contains instructions for resetting the device and for all external communications the chip might make. Serial flash, also known as NVM, non-volatile memory. The MC1322x's non-volatile memory is the serial flash. The serial flash is 128 kilobytes. 96 of those kilobytes go to RAM for purposes in the main program code, and the excess 32 kilobytes are used for other purposes. 4 kilobytes are reserved for factory use, but the other 28 kilobytes are used for non-volatile data storage and optional application profiles. The serial flash is accessed through a Serial Peripheral Interface (SPI) module, designated as SPIF. Through this synchronous serial interface, the flash, erase, program, and read capabilities are all programmed. At boot time, the flash contents are accessed in order to load or initialize RAM for the program's execution. Flash is also accessed in order to reinitialize or restore RAM that had been unpowered during sleep. The serial flash can be also accessed through the program control, and it includes an SPI serial interface with 13 MHz maximum clock. A driver for flash access is available and can be integrated with the user's application. This is for erase, program, and read. The flash data can be made secure for the boot process. JTAG or Nexus interfaces start out disabled. The bootstrap then determines if the flash is secure. This is done using the first 4 bytes of the flash, which are reserved for the validation word. If the validation word is OK, then the data is valid, but not necessarily protected. If the validation word is SECU, then the data is both valid and secure. The JTAG or Nexus interfaces are only enabled if Bootstrap determines the flash is not secure, or they are re-enabled by forcing the flash to be cleared. The flash can also be erased through the boot process in order to be recovered to a known condition. Erasing part or all of the flash is also possible through program control. Now for some general information on Parallel Input I/O (GPIO). Let's first break down the term GPIO and Parallel Input Output. GPIO stands for General Purpose Input Output. It's a pin on an integrated circuit that doesn't have a specific function and connects microcontrollers to other electronic devices. The function of a GPIO is customizable and can be controlled by software. One popular example of a GPIO is the Raspberry Pi. The Raspberry Pi is a single board computer that includes a row of GPIO pins along the edge of the board. These pins provide interface between the Raspberry Pi and other components. You can connect a device to certain GPIO pins and control it with software program. An example is wiring an LED to a GPIO, and if the program tells the GPIO pin to turn on, the LED will light up. Now for some parallel input-output. Parallel I/O means performing multiple input-output operations at the same time instead of process I/O, which means one at a time. This lets a system have higher write speeds since there's multiple input-output. An example is simultaneously outputting to storage devices and display devices, which is a feature of an operating system. Now that some of the general terminology has been established, we'll get into the specifics of MC1322x parallel I/O GPIO. It consists of 64 GPIO pins. It contains 4 JTAG IOs, 22 GPIOs as interfaces to peripherals, 8 dedicated KBI, which stand for Keyboard Interface GPIOs, 8 ADC, which stands for Analog to Digital Conversion analog inputs, 4 control pins for external radio frequency control, and 14 Nexus pins, which are JTAG as well. The picture on the right shows these pins, and in chapter 2.2 of manual gives specifics of each pin and what they do. The general idea is that there are multiple keyboard interfaces, timers, analog to digital converters, JTAG, which allows data transfer into internal non-volatile device memory, and radio frequency transmission, and UART. The MC1322X also consists of software-controlled pull-ups or pull-downs on all pins. A pull-up resistor weakly pulls the voltage of the wire it is connected to towards its voltage source level when the other components on the line are inactive. When the button is pressed, it connects the input pin directly to ground and current flows through the resistor to the ground. A pull-down resistor works the same way except it's already connected to the ground. In the MC1322X, each GPIO has a selectable pull-up pull-down resistor. The pull-up pull-down is only enabled when the pad is an input. It is disabled when the pad is programmed as an output. Each input-output port is a single bit and is easily configured. The port has a set of data and control register bits that determine the operation of that port. For 64 ports, two 32-bit wide registers of each type are used except the function select control. The function select GPIO module has 4 modes: normal, alternate 1, alternate 2, and alternate 3. Normal mode puts all the I/O to GPIO mode except the JTAG pins. When one of the alternative modes is enabled, the ADC, analog to digital conversion module, puts its pads into analog mode and the digital pad function is disabled. The specifics of each mode are found in 11.4.1 in the reference manual. UART. What is UART? UART stands for Universal Asynchronous Receiver and Transmitter, also known as RS-232. It transmits bits serially at a mutually agreed speed without the use of a clock. The speed is known as baud rate. The UART provides the computer with the RS-232C data terminal equipment interface. It allows communication to the modems and other serial devices. The UART converts the bytes it receives from the computer along parallel circuits into a single serial bit stream for outbound communication. On inbound communication, the UART converts the serial bit stream into bytes for the computer to handle. It also handles interrupts from user devices such as keyboard. It has the ability to handle other forms of interrupts which require coordinating the process speed with the device speed. It does this by buffering the data so that the computer and serial devices are coordinated with one another. Most modern internal modems most likely include a 16550 UART. The 16550 has a 16-byte buffer which assists the processor because it can be filled before the processor needs to handle the data. The steps of UART transmission are as follows. Step 1. The transmitting UART receives data in parallel from the data bus. Step 2. The transmitting UART adds the start bit, parity bit, and the stop bit to the data frame. Step 3. The entire packet is sent serially from transmitting UART to the receiving UART. The receiving UART samples the data line and the pre-configured baud rate. The receiving UART discards the start bit, parity bit, and stop bit from the data frame. Step 5. The receiving UART converts the serial data back into parallel and transfers it to the data bus on the receiving end. Timer module. The timer module is used to count internal and external events and reconcile these values with predetermined values. External inputs are shareable, can be used for both timer and counter purposes. The module has 4 external timers, input-output pins, and each counter timer has a variety of function modes in which it can operate. There are 3 primary functions for the timer module. The first is input capture. According to Wikipedia, input capture is a method of handling and directing input signals within an embedded system. A chip like the MC1322x is often used for embedded systems, which will mark a received input signal by recording a timestamp in memory. Another function of the counter and timer groups is output compare. Output compare, according to Wikipedia, is the ability to trigger an output based on a timestamp in memory. With output compare, you can do this without pausing the microcontroller's other processes, like code execution. The last primary function is pulse width modulation. This function refers to the ability to encode data within a pulsing signal. The timer module can also handle 3 kinds of interrupts. The first is a timer compare interrupt. This happens when a match occurs. The second interrupt is a timer overflow. This happens when a counter exceeds its maximum preset value. The third and final interpret is the timer input edge, which happens when the input signals transition from one to another. The final key thing to mention about the timer module is the types of registers that are included in each counter timer group. These include load registers, hold registers, capture registers, compare registers, and status and control registers. This presentation looks into the complex but essential architecture of a microcontroller, which is helpful in understanding the capabilities of the device and the role this chip can play in the larger technology landscape. Microcontrollers are extremely valuable for embedded systems, especially as Internet of Things devices grow more prevalent. The small physical scale and relatively high performance capacity of this microcontroller allows for better use of computing resources and independent but intelligent devices. Additionally, these devices can serve as an education tool for makers and those in tech fields. it may be easier to conceptualize a computer system on this small scale while also seeing how powerful a small device can be. That will conclude our presentation. Thank you.